So, okay, so let us begin. Welcome to the week 4 tutorial for solid mechanics NPTEL course. So, this week the Professor Ajit covered, I think, concepts of longitudinal strain, more stress plane, then how any general state of stress can be decomposed into hydrostatic and deviatoric parts. Okay, so we have been given some problem data for the first 4 questions, and it states the following: sigma xx equal to 14 Pascal, sigma yy is 0 Pascal, sigma zz is 18 Pascal, tau xy is 24 Pascal, tau xz is 0, and tau yz is also 0. So if I write this stress tensor in matrix form, I will get 14, 24, 0, 24, 0, 0, then 0, 0, 18. So this is the state of stress tensor sigma written in the matrix form for XYZ coordinate system. The annotations are visible, right? Are the annotations visible? Can someone please unmute themselves and confirm?
Yes.
Okay, good. Okay, so we have written the state of stress, and right away we can make a few observations. Firstly, it seems that there is no shear component on the z plane, so we can say that z is actually aligned to one of the principal axes, say n3. Z axis is aligned along one of the principal axes. So for this particular information, we can draw a Morse circle. Since this is satisfied, we can draw a Morse circle.
Sir, can you please explain what is hydrostatic part and deviatoric part? I can't understand in the lecture.
Okay, so so basically what we have is, one second, I'll go to the end. There's a blank slide. Yeah. Okay, so normally you'll have a stress matrix as sigma sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 3 1, sigma 2 2, sigma 3 2, 2 3, sigma 3 3. This is your normal stress tensor written in the matrix form. And if we plot this on the body, we'll have like shear components and normal components on all the 6 faces of this cuboid. Okay, so this is E1, E2, and E3. What the deviatoric and hydrostatic part essentially try to do is we try to decompose this sigma as a sum of sigma h plus sigma d, such that for the deviatoric part there is no normal stress. Like if I write this in matrix form, I this should be 0, and for the hydrostatic part there is no shear. What we saw from, like when we looked at the stress invariants, what we saw that if we have lambda, which are the principal stresses corresponding to some stress tensor sigma, then after rotation the principal stresses that you get are still unchanged. So if you remember, we write this as sigma is R transpose. Sigma cap is R transpose sigma R. And when we write it in its characteristic form, we essentially end up with lambda cap equal to lambda. Now, this is like, this essentially tells us that rotate, we can rotate, go to any new different coordinate system, and we'll still have the same principal stresses. So once this is clear, so if we write it in the coordinate system corresponding to the principal planes, you will end up with something like this. Now what we do is we rewrite sigma as 1 by third I1 of sigma into identity tensor plus sigma minus 1 by third I1 of sigma into the identity tensor. If we look at the first invariant for this matrix, which I'll name for this tensor sigma h, we see that I1 of sigma h is nothing but I1 of sigma. And this clearly is a diagonal matrix. This is a diagonal matrix. In matrix form, this is diagonal. Not this one, sorry. It should be lambda 1 plus lambda 2 plus lambda 3 by 3. Then lambda 1, 2 by 3, and so on. Whereas for this matrix, if I rename this as sigma d, if I look at its stress invariant, then it is nothing but 0. So we essentially say that we do some unknown rotation transformation R, which will convert the diagonal terms here to 0. Sorry.
How the second part has become zero? Like in sigma tensor matrix in
Mm-hmm.
diagonal, we have like let us consider some sigma 1 1 and sigma 2 2 and sigma 3 3 as a diagonal.
Mm-hmm.
But in that minus of we have something sigma 1 plus sigma 2 plus sigma 3 by 3. That is what when we do minus with sigma 1 1 minus of 1 by 3 of sigma 1 1 plus sigma 2 2 plus sigma 3 3 is not equals to 0 now.
But you forgot that this has a trace of 3. So you are correct. This has a trace of sigma 1 1 plus sigma 2 2 plus sigma 3 3, which is nothing but your I1 for this matrix. For the I, which is the identity tensor, your I1 actually turns out to be 3, whereas this portion is simply a scalar, which is equal to sigma 1 1 plus sigma 2 2 plus sigma 3 3 by 3. So when you take I1 of this entire matrix, say A minus B, then you'll end up with this value minus thrice of this value, which is essentially 0. Okay, or is it still not clear? So, so after some rotation, we end up with this is essentially sigma h, only the diagonal terms. So sigma h can be written as sigma 1 1 plus sigma 2 2 plus sigma 3 3 by 3 into say 1 0 0 0 1 0 and 0, 0, 1. So as you can see, this is purely a state of normal stresses. So this part of the stress tensor will only cause contraction and relaxation. Sorry, elongation and compression. Whereas if you look at the remaining part, after some rotation R, you will end up with only shear parts. So what you have is sigma h, which is causing same like a volumetric contraction or expansion in all three directions together, like a hydrostatic. Like, the reason they call it hydrostatic is this is very similar to what you see for a fluid at rest, which is minus p0, 0 minus p0, 0, 0 minus p. In for fluids, this will be only like compressive, but for solids, this value can also be positive. So you can have a uniform elongation in all three axes. Whereas this other part, deviatory, it essentially causes only shear remains. So you essentially get a distortion of the cuboid. So one will increase or decrease the size of cuboid, other might make it into a parallelepiped. So any random state of stress can essentially be seen as a sum of those two. For fluids at rest, there is no deviatoric stress. There is only hydrostat part. So for fluids at rest, you will only have like a compression with pressure P. Okay. Shall we go back to the problems, or do you want me to try a different way, or do you have any other doubt? Okay, well, we'll go back to the problems. This is the state of stress that we have been given. So 14, 0, 18, and 24 on xy, 0 on xz, and 0 on xy. So straight away we can see that the z-axis is aligned along one of the principal plane normals, say n3. Therefore, we can apply the concept of Moore's circle. So the center of the Morse circle is given by sigma c equal to sigma xx plus sigma yy by 2, which is nothing but 14 plus 0, so 7. So your center is at 7, comma 0. And your sigma xx, which is 14, so 7 more in this direction, and tau xy is 24. So this is 24. So this is 14, comma 24. And this should be 0, comma minus 24. This is E1, this is direction E2. Now these are the details that we know. We don't know lambda 1, lambda 2. We can quickly calculate what the radius is from this. So R is essentially sigma xx minus sigma yy by 2 whole square plus tau xy whole square, which is nothing but root of 7 square plus 24 square. This is 25. So this is your R, and you can therefore write lambda 1 comma 2 is sigma center of the circle plus minus R. Therefore lambda 1 is 7 plus 25, which is 32, and lambda 2 is 7 minus 25, which is minus 18. So we have calculated this much so far. Let's look at what questions do we have. Okay, the first one is pretty straightforward. Center of Morse circle, as we did, sigma centroid is nothing but tau centroid will be 0. Sigma centroid will be sigma xx plus sigma yy by 2, which is nothing but 7. This is clear, right? Very straightforward. And again, okay, so I think I already calculated these things. Radius of the Mohr circle is root of sigma xx minus sigma yy by 2 whole square plus tau xy whole square, which is nothing but 14 minus 0 by 2 whole square plus 24 square is 49 plus 576 is 625, so 25. This is also straightforward from the formula. Okay, which of the following is true regarding principal stress components for the given state of stress? So can anyone tell how many principal stress components we know here? Do we know like two, or do we know three?
3.
Correct. Can you explain why?
Because 2 we can get from Mohr circle, and the other one it is already oriented. From the matrix we can get 2.
Correct. So to rephrase what you said, Mohr circle is applicable only when one of the directions is aligned along one of the principal plane normals, which is what we see from sigma zz. So sigma zz is non-zero. This is equal to, is it equal to 18? I think. Yeah, this is 18, which is what we know, and tau xz equal to tau yz is 0. So this is a principal, z is a principal plane normal. There is no shear component, and the other one, lambda 1 and lambda 2, can be determined by stress at the center of the circle plus minus r. So we know sigma c, we know r, and we know sigma zz. So we know all three values. Can someone quickly tell what they are?
Option D.
Yeah, correct. We already calculated lambda 1 to be equal to 32, lambda 2 to be minus 18, and sigma zz equal to lambda 3, which is 18. So, okay. So as you can see from this question, so if you are anyways, if the condition for Mohr circle is satisfied, you not only know the principal stress component, but you also know their directions as well. So everything is in a sense known. But if in general this is not aligned and you want to calculate what the principal stresses and what the principal plane normals are, then you have to solve this eigenvalue equation. So this is a cubic equation. Mohr circle essentially helps us to reduce this to a quadratic. Okay. And finally, the value of octahedral state of stress. So what is the formula for octahedral stress?
I 1 by 3.
Correct. I1 by 3. Which is, for this case, I1 is nothing but lambda 1 plus lambda 2 plus lambda 3, which is sigma xx plus sigma yy plus sigma zz, which is 32 minus 18 plus 18. So I1 is 32. Therefore, sigma octet is 32 by 3. This can also be written as lambda n square. Sorry, this is correct only, lambda n square. So yeah, okay. Hmm.
Hello.
Yeah.
Regarding octahedral stress,
Hmm.
during the lectures, it was told that during while calculating principal stress that it is used for failure theory.
Hmm.
What about octahedral stress? Is there any significance for that also?
So invariants in general are useful in different cases. So like you can see, the sigma octahedral, which is I1 by 3, is nothing but the hydrostatic part of your stress. So if say one of your failure theories deals with a limit to the hydrostatic part of stress, then this becomes useful. There are some failure theories which deal with the maximum shear, say tau max. In that case, your deviatoric part becomes important. So this is also important. This is nothing but your, if you remember, this is nothing but your hydrostatic part of stress, right? Ideally, for if we want to stay in elastic regime, we'll say that your maximum principal stress should be limited to certain value, say the yield stress. So okay. The fifth problem, it's a simple true or false problem. When two of the principal stress components become equal, the three circles in Moore's stress plane reduce to a single circle. So Moore's stress plane is like this. This is your general Moore's stress plane. And we are given that two of the principal stress components become equal. Say lambda 1 becomes equal to lambda 2. Then this will automatically reduce to a simple Morse circle. This means that if we plot the normal and shear components of traction corresponding to all planes at that point, those points will lie inside this circle. Is the statement true? Will the points sigma comma tau lie inside this circle? Sorry, I didn't hear you. Can you repeat?
False.
Yeah, false, correct. As this keeps on shrinking, you would end up with, say, something like this, and the area will become smaller and smaller till till what actually remains is just like the line of the circle. So it will lie only on the circle. I have a quick question. So I think Professor must have mentioned in the lectures that we do not look at points inside here, right? We only look at the points in between this circle. Does anyone know why? Like these points are not allowed, right? Only these shaded region points are allowed.
Because lambda 2 is saddle point.
Yes, lambda 2 is a saddle point. What that would mean is that it's not a maxima or a minima. So both to the left. Okay, sorry. Sorry for that. Yeah. So lambda 2 is a saddle point means that if we approach lambda 2 from like sigma less than lambda or sigma greater than lambda 2, these points still exist, like very close to lambda 2. Both of these points exist, whereas for lambda 1 only sigma less than lambda 1 exists. For lambda 3 only sigma greater than lambda 3 exists. So last week we had this question which asked if sigma xx is always less than all of lambda 1, lambda 2 and lambda 3, which we found out to be false, which is also seen from this Morse stress plane. Saddle point is correct, but that still doesn't answer, because if I look at, say, this point, it's for this point sigma is less than lambda 2, for this point sigma is greater than lambda 2. But we still do not use the points inside the circle. Do you have any idea, like, if you had to go about proving this, how would you? If I have any general state of stress, if I look at any general traction, Tn is, say, sigma n, I can decompose, I can use this to find sigma nn, which I rewrite as sigma, is Tn dot n. If I use a coordinate system which aligns along the principal axis, then my sigma would be lambda 1 0 0 0 lambda 2 0 0 0 lambda 3, and I enforce the condition that lambda 1 is greater than lambda 2 greater than lambda 3. Then if I have to write sigma, it will essentially become lambda 1 n1 square plus lambda 2 n2 square plus lambda 3 n3 square. And if I want to write the traction Tn, it becomes lambda 1 n1, lambda 2 n2, lambda 3 n3. And if I take the modulus of traction Tn, it is nothing but sigma square plus tau square. So sigma square plus tau square is lambda 1 square n1 square plus lambda 2 square n2 square plus lambda 3 square n3 square. This is, say, equation 2. This is equation 1. And finally I have a constraint, n1 square plus n2 square plus n3 square equal to 1. So I have three equations, and if I take n1 and n1 square, n2 square and n3 square as my n1 square, n2 square and n3 square as my unknowns, I can rewrite this. If I take these three as my unknowns and try to solve, I'll end up with a bunch of equations, and then I apply this condition that ni square must always be greater than 0, as greater or equal to 0. So these equations 1, 2, 3, apply constraint ni square is greater than 0, and what you would see is something like this: sigma minus lambda 1 plus lambda 3 by 2 whole square plus tau square is less than lambda 1 minus lambda 3 by 2 whole square, less than or equal to. So this is saying that your sigma and tau must lie in a circle of center lambda 1 plus lambda 3 by 2 and radius given by lambda 1 minus lambda 3 by 2. I think this equation comes for n2 square greater or equal to 0. Similarly, I get another inequality when I write ni square greater than 0. It is sigma minus lambda 2 plus lambda 3 by 2 whole square plus tau square is greater than or equal to lambda 2 plus lambda 3 by 2 whole square. This says that sigma and tau must lie outside the circle lambda 2 plus lambda 3 by with center lambda 2 plus lambda 3 by 2 and sorry, radius lambda 2 minus lambda 3 by 2. So it must lie outside this circle. It must also lie outside this circle, and it must lie inside the big circle. You can try this out as an exercise and see if you actually get whatever I'm saying, and maybe post it on the discussion forum. It might be an interesting way. Or if you can think up of any other way which gets us to a similar conclusion without having to say go through this much effort, that would also be appreciated. Try this out. I would say it's very interesting. At least I found it to be. Okay, the sixth problem. Suppose the trace of a stress matrix. So trace of stress matrix. This is 0. Then which of the following must be true? Can anyone say which of these do you think are true?
Right part.
Sorry?
The hydrostatic part will be 0.
Yes.
Electrostatic will be absent.
Correct. So the since trace is 0 and trace is nothing but I1, we can say that I1 of sigma, the first invariant of sigma, is 0. And the hydrostatic part, if you remember, is nothing but 1 by 3 times I1 of sigma times identity tensor. If this is 0, your sigma h is also 0. So the hydrostatic part is 0. The first invariant is 0. Can we say anything about the second or the third invariant?
Might be non-zero.
Yeah, it can be non-zero. We cannot definitively say that they will be 0. So the first two options are true. Okay, the seventh problem. It's a simple true or false statement. You have a unique value of longitudinal strain at every point in the body. Is this true or false? So if you remember, we write longitudinal strain as something like this. Obviously false, right? Because even if you fix x, you can move around with. Even if this is fixed, you can move around which direction you want. This is very similar to what we saw in traction, t of x comma n. So since you can have infinitely many planes passing through a point, you can have infinitely many traction values. Similarly, you have something for the longitudinal strain. Like even if you fix a point, you can choose and like infinite directions through that point. This is obviously false. Okay, so we are now given a displacement function. U of x is x1 minus x2, x1 plus x2 0, and we have to find the components of deformation gradient at some location x. Okay, so does anyone remember how we calculate the deformation gradient in terms of displacement function u?
I plus gradient of displacement.
Correct. This is identity plus gradient of displacement. This is simply 1 0 0 0 1 0 0 0 1, and gradient of displacement would be a matrix of the form dou ui by dou xj. So for this particular displacement function, we can write gradient of u as dou u1 by dou x1, dou u1 by dou x2, dou u1 by dou x3. Okay, why do we write this in a row and not like a column? First of all, is this correct? Do I write this as a row or do I write this as a column?
What you're writing is correct.
So why do we write this in this way? Like how do you know? Like one way to go about it is like remembering this, that it is dou ui by dou xi and not dou uj by dou xi. But do you like remember this, or do you remember all the terms, or do you remember some simple logic?
Actually, we have formulas now, sir, for gradient of f.
Yeah, so if you want to see a small displacement, you'll write something like f delta x order of delta x square. This is correct, right? This formula. And you can write delta x as nothing but delta x1, delta x2, delta x3. This is a column vector. So essentially, when you want to find the gradient and you multiply it with this column vector delta x, you'll end up with, if I do grad u times delta x, I'll end up with estimates for delta u1, delta u2, delta u3. Okay, so if I'll continue this here. So dou u1 by dou x1 is nothing but 1. Dou u1 by dou x2 is minus 1. This is 0. Dou u2 by dou x1 is 1. Dou u2 by dou x2 is also 1. Dou u2 by dou x3 is 0. And since u3 is 0, all these three are also 0. So my f, combining these two, my f would become 2 minus 1, 1, 2, 0, 0, 0, 1. This is my f. As you can see, because of u being a linear function in displacements, this is independent of whatever location you take. And so we have f of 1, 2 is minus 1, f of 3, 3 is 1. So these two are the correct options. Okay. Right. The ninth problem. Which of the following is true? So gradient of a scalar is a second order tensor. Gradient of a scalar, is it a second order tensor?
No, gradient of vector is a second order tensor.
Correct. Gradient of scalar would simply be a vector of this form. So gradient of a scalar is a vector which essentially is a first order tensor, whereas the gradient of a vector is a second order tensor, as we just saw. Gradient of V is a matrix of the form dou Vi by dou X. Okay. The last problem for the day. Consider a 1D problem where a horizontal bar is stretched by the application of an actual force. An actual force F P is applied. Length of the bar was initially 1 meter and final length of the bar is 1.1 meter. So which of the following statements are true? Can we find out this?
Option B.
Sorry,
Option B. Stretch of the bar is 1.1.
correct. Stretch of the bar would be final length upon initial length, which is nothing but small l by capital L, which is 1.1. Okay. So, right, these are the questions I had for this week's session. So, apart from this problem on deviatoric and hydrostatic stress, what I'll try to do on my end is try to find some values where I can actually derive this and share this with you on discussion forum. And what I would like you guys to do is try to solve this one, like try to prove that we don't use any points on the inside. I've already given you the equations and what I think should be the final form of the answer. But if you can verify it on your own, it will be great. So till week 4, I think it was mostly we were mostly looking at stress only. Now we have started looking into strain. So have you guys started doing the week 5 lectures? So okay, so those lectures are quite important because they'll cover the concepts of longitudinal and shear strain. So they are analogous to what you have like normal and shear stresses in the concept of a stress tensor. And the assignments, are you able to do them? Are the assignments, how are you finding them? Are they okay? Are they difficult? Or are they too easy? Okay, so do you guys have any other doubts?
So we're calculating shear strain. We have formula now, like
Hmm.
2 times of strain tensor matrix and n vector dot m vector.
Hmm.
In that n vector dot m vector, like I have to take two perpendicular axes measure. If I
Hmm.
reverse the two axes, like for one time I'm taking one e1 as a n and
Hmm.
e2 as a n.
Hmm.
For another time I'm taking e2 as a e2 as a n and e1 as a m. Can answer be changed? Is there any possible to change? Like we are multiplying that one with two times of strain tensor matrix now.
Yeah, so is this what you are referring to? This, I think this is what you are referring to, right?
But will be yeah, 2 into 1 now. Okay.
Right. Some given location x and two perpendicular directions m and n. Then you find out the gradients multiplied with m. Yeah, so your doubt is, sorry, I didn't clearly get it. So what you are saying is first we do m and n and then we do
Then
n.
if equation, we need two perpendicular lines, sir.
Yes.
If I take E1 as a M and
Hmm.
E2 as a N
Hmm.
in one calculation, and in
Hmm.
another calculation, I'm taking reverse, like M as a E2 and N as a E1. Do my answer change?
No, they'll be same because you are looking at the, say you are looking at the magnitude. So say E1 will go to this after deformation, E2 will go to this. What you are calculating is like these like change in magnitude of 1 and change in magnitude of 2, and you are summing them up. Like this is, I'm trying to explain this physically. So if you think about in this way, your answer should not change. If for some reason you are, say you are get, if for some reason you are getting alpha mn not equal to alpha nm, then I think you have a problem.
So
Did you say something I didn't hear clearly? So if I look at, I'll I'll say label this as A. You can clearly see that if I take A transpose, then it's nothing but A. A transpose is nothing but A. So A is a symmetric matrix. And this dot product can be written as N transpose A M, and for alpha M, for alpha N M, this product will be an dot m, which is not, which you can write, which you can also write as na whole transpose m, which is nothing but n a transpose m. But since a is symmetric, this actually becomes n a. Sorry, this actually will become the same thing because a is symmetric. A transpose is a. Is this clear? it it depends essentially on this, because you have grad u plus grad u transpose, this whole matrix would essentially be symmetric, and because of that, no matter what order you take, if it was not symmetric, then you would have a problem. This should be, sorry, n transpose, I'm taking transpose, n transpose a. Okay,
yes,
right. So yeah, so that is all I have for today. If you have, if you have no more doubts, then we can stop. Yeah, so thank you for, do you have any doubts?
Could you suggest a book for additional problems, please?
Okay, I actually like LS Srinath, which is what has been told as the textbook, but there are some more books which are a little more elementary and easier. So I'll post their names on the discussion forum if that's okay.
Yes.
Okay, I'll also, the Timoshenko one has professor suggested the Timoshenko Strength of Materials book. That is also a very good book. It has, I think it doesn't have as many problems, but as far as concepts go, it's a very well written book. It's, I think, better than LS Srinath when it comes to how the concepts are explained. Okay, I'll post a couple of references on the discussion forum for problem solving. Okay then, thank you for attending, and I'll see you next week.